It's of course a great pleasure to be here in the center of network science. And I would like to talk, like Alex said already, about diffusion processes actually on one simple model, and that's the SIS model. That's an oversimplified model, and on networks. And the talk I'm going to give is, that's the exact prevalence, and then I talk about the tanh-formula and the new work which is unpublished and which I try to share with you that's completely new. And I hope it's a bit inspiring. So let us first see, as a definition, what is the SIS model. I think most of you know it, so I can go a little bit farther. So basically it means that we have a continuous time, I consider continuous time Markov process, in which you have nodes in the network, right? And if you are healthy, you can get infected by your neighbors with the rate beta. And only when you are infected, after some time, you can get cured with the rate delta. So very, very simple. I only have two parameters given a network infrastructure, any topology represented by an adjacency matrix, and then I have a simple, very simple local rule, what I call, right? And you know that there are a lot of interesting physical models that are based on these very simple local rules, yet they actually give rise to an emergent behavior which is amazingly complex, yeah, with phase transition and this model is what I think the simplest model, which is showing still this continuous phase transition. And why it's the simplest model? Well, I try to persuade you because you can do analytic work on that one. I assume also that the ratio between the infection rate beta and the curing rate delta, that's the effective spreading rate. And I'm not going to talk about non-Markovian behavior, I just take Markovian processes because they are way simpler than non-Markovians. So I assume that the infection and the curing process are independent Poissonian processes. Okay? So that's the setting, that's the definition of the model. I assume that the network can be in two states. Any node can have two states, either infected and then you have one. Then this random variable is then one if it is infected at time t, and otherwise it's zero and it's not infected. That's an important thing, because this is what we call in mathematics, that's a Bernoulli random variable. Again, that's the simplest possible random variable, right? It can only have two states, 0 and 1, with a certain probability. Okay? So, let us now immediately give you the governing equation, which gives you the dynamics of an epidemic from a local point of view. You see? I use probably not quite physical interpretations, but I show you the power of having the expectation generator, and here inside you only have random variables. What does it say? It just says that, let me first, we are interested in the differential equation, so this is the time, change of time of the probability that you are infected. You see, one of the very important things which I keep stressing again is, if you have a Bernoulli random variable, you don't need to deal with probabilities. Yeah? The probability operator is in most cases a very complex operator. However, the expectation is a linear operator which is very easy, right? And if you rephrase the total set of equations just in the expectation operator, you're easier, right? And that's what we do. You write this expectation, and then you try to see what is the change in your probability, and that is the expectation. You model out the expectation, and then you just have the physics written plain in random variables. And it says you have two processes that are competing. The first is a process if I, as node G, I'm infected, so my state is 1, right? Then I can cure with the rate delta, and the curing means it's negative. It means that my probability of infection goes down, right? So it's a negative sign. Very easy. And only this can happen at that time. Why? Because here it is 1 minus. And either I'm healthy, right? If I'm healthy, I'm here. Basically, then it's 0, that this plays a role. And when I'm infected, this is 1, then this plays a role, right? So this is the simplest term. The more complex term is this one. If I'm healthy, so my status is 0, so this random variable is 1. I can get infected by all my infected neighbors, because this is an adjacency element, over this sums over all the possible neighbors that I have, and these neighbors should be infected, right? Okay, that's the basic physics. Very simple, okay? That's what I explained here, infected probability. Now, if you now move in the operator, yeah, the expectation operator, you see that the whole complexity is coming from this term. Here you have the network, and you have here actually a product. It's quadratic in the random variables. And if you work out that product here, you move in the linear operator, then you have this kind of an equation. It's quite well known. And this equation is what people call in physics not closed. You know, not closed, because it's a differential equation in this random, well, in this quantity, the expectation or the probability that you are infected. Yeah? And you see that that quantity appears here. However, here we have a problem, because the quantity does not appear anymore. Yeah? So then there are two possibilities. Yeah? Either you try to deduce other differential or other information about the correlation that two neighbors are infected. Yeah? You write them down, the equations. You can do that. You can do writing these equations down, then you have an older system of equations, but then you have not n equations, because capital N is the number of nodes in my network, and here I have n nodes, but then you have n over 2 binomial and n over 2 square, well, n square order correlations and so further. So in total, if you go further, you can deduce it in that way, and then you end up with 2 to the power n linear differential equations. It's important that you have linear n. Another way what I'm going to do in this talk is I'm going to use a kind of an approximation. I try to close the equations. And closing the equations is that you try to express the term that you don't know in terms of terms that you know. Okay, that will be a basic thing coming on later. So first of all, I'm now only going to consider the simplest of the simplest again of the SIS process. And that's very important to understand. I'm only going to talk about a fraction of infected nodes in the network. Yeah? And I define that the fraction or the sum, right? You sum over all the nodes that are infected and you take the ratio. So this is a random variable between 0 and 1. And that's called the fraction of infected nodes in the graph. So this is a random variable. And the prevalence, what we define, is basically the expectation of that random variable. That is the expected fraction of number of nodes in a network that is infected.
On the previous slide, if they are not correlated, what happens?
This term.
Yeah, if you just like write it down as a product of expectations, then what's happening?
Well, I will show this immediately later on. I will show that the whole complexity basically writes in this term. So this is the definitions. This is quite straightforward, and I think this is, if you have a network that is infected, well, there is an epidemic, the simplest question is just the prevalence, right? That's the basic first question that you ask. Okay, let us now see how you actually can find the differential equation for the prevalence. I gave you the differential equation from the nodal point of view of a node that is infected. Now you do the prevalence. So I started with, of course, the nodal view. That's what I just have posed to you, try to explain it. That's the differential equation from the probability that node G is infected. And now I'm going to derive summing over all the nodes. Yeah? So again, I use explicitly the fact that I have an expectation operator which is linear, so I can easily sum these equations by taking out my summations, interchanging with the expectation. So if I do that, right, I get this term, and then I have here a summation, I basically divide everything by delta. I put a delta here, and delta divided by beta is tau. Yeah? So then I have this kind of a step. Okay, then I use the definition of the prevalence. I just say that the prevalence is 1 over the expectation of this one, and you see that term appearing here, you see that term appearing here, and I move in the expectation. And then I have here an ugly quadratic form, and if you know a bit about linear algebra, you can write a quadratic form in a very effective way. And that's the way in which you have here the nodal random Bernoulli vector, that is the W vector, which all the states of all the nodes, whether they are infected or not. And U is the 1, 1, 1 vector, so this is the complement, basically, of that vector. Right? So if you fill in from here you sum, you immediately get the exact form of the differential equation at a scaled time. I scale the time by delta multiplied by t. What's here? I call it t cross. Then I have this kind of differential equation. And you see, this term is again from the same type. However, the term here, due to the network, is not of the same type. And that's the complicated factor, right? I'm going to simplify this factor a bit by assuming that my network is just symmetric, bidirectional, right? If it is bidirectional, then you see that you can write everything in the Laplacian and you have a very beautiful, I like this formula. Actually, this is a very beautiful formula. Think about it, this is an exact description from all networks and it gives you the prevalence as a function of time, just in function of the expectation of a quadratic form of a Laplacian. Beautiful, huh? So I'm going to talk about this form the rest of the talk, just to understand now physically what it means. I now gave just the mathematical derivation, which is probably for most of you not so cool, but now I try to understand what that means. Yeah? So the first thing what I said is I started the definition or the talk by saying we have a local rule, and this is the local rule which I explained. If you have a local rule, then we derive basically here now the global emergent effect. Yeah? Here you have the local rule, where you see a little bit here the network coming in, and here you have then the global, the network view, where here you see via the Laplacian, yeah, completely the structure of the network. So if you think that there are phase transitions, or if there are very strange phenomena going on, they should be actually visible here by understanding that differential equation. Okay? So let us now see what that means. If you have a set of infected nodes at a time, a scaled time t star, right? Then, well, here I have 7 of these nodes, and then normally you have then in the network, hopefully, another set of nodes that is not infected. So this is then the set of infected nodes at the same time. Yeah? Then we see here that the links between those two sets, this is the set with infected, non-infected, and these we call actually infective links. Yeah, these are the links with one neighbor which is infected and the other neighbor not infected. And this is what we call the cut set. Yeah? And the cut set basically, you can calculate, this is the Bernoulli random variable which is 1 and zeros. And if you compute this quadratic Laplacian form, then you find precisely in this case 6. So this basically means the average over the infective links in my network. Now, at each moment of time, we see that you have a curing process with the rate 1, because I normalized the time that my delta, my infection rate is 1. And then the more complex term, which is the driver of the epidemics, lies in the number of infected links only in the cut set, right? So here, they are infected, you don't see any change. And here they are healthy, you also don't see any change. Thus, the difficulty of the process lies in the cut set, between infected and non-infected. And again, I call these links, the red links, infective links. Yeah? The links where actually your infection is going to travel over from the infected cluster to the non-infected cluster. Okay, let us now first see how we can push a little bit the analysis further. I'm going to present you a tangents H formula, right? What we define based on the exact formula. And let us do, I use spectral decomposition. So I have here my Bernoulli random variable with all the infections of the nodes. Each of the components is either 1 or 0, right? And then while I'm doing this, I'm going to expand that vector in the eigenvector structure of my Laplacian. That you can always do, right? Because my eigenvalues. And if you do this, you fill it in, you get a kind of expression of my form here, which is the number of infective links in my network. Remember, the number of links over which my infection goes. And I express this in the spectral domain in function of the eigenvalues of my Laplacian. And here, the zeta is actually the scalar product of my Bernoulli vector on the eigenvector component x belonging to the eigenvalue mu x of my Laplacian. Okay? So if you use now nice Bernoulli properties, yeah, why are these nice? Because you know that the norm of my Bernoulli random variable, which is a 0, 1 vector, is equal to the number of ones. Yeah? And using this one, I have an additional equation, which is implicitly hidden in the structure. Yeah? And if you use that, then you can show that this form, on which you can't say too much, yeah? But if you use that kind of an information, quadratic form, you can write that form exactly in this term. While this is the smallest non-zero eigenvalue of the Laplacian, which is called the algebraic connectivity. Yeah? And the algebraic connectivity physically says how difficult it is to actually intertwin or interconnect or disconnect a graph into two parts. Yeah? And here you see S, this is my number of, the fraction of infected nodes. These are still random variables. And R, of course, is the difference what we have. R is a complex thing. You see it? You can write R in this form, still exact, and you can show that it's always larger than 0. That's interesting. But what is even more interesting is that R factor is completely 0 for a complete graph. Okay, take that with you. In a complete graph, this is 0, and the number of infective links is exactly calculated by this expression. Again, this is a random variable. This is not an expectation, no probabilities. This is just a random variable. At each moment of time, you have precisely the number of infective links written in this equation. Okay? Good. Remember that that was the that was the differential equation of my prevalence, yeah, in which this term, the infective things appears, but there was also an expectation. And what I'm now going to do is just to substitute that random variable, what I found, into this one, and then I come up with this differential equation, which is still exact. Yeah? But I still have here now a difficult term. The difficult term is, I call it psi, is due to the fact that, well, I have here, well, a difficult form that measures basically the differences from a complete graph, right? And here a variance term. And this is difficult. So at this moment, I don't think that people can push the analysis much further, right? And what you do, if you can't push it much further and you have here a term what you don't want, you think deeply and you say, well, probably I can't ignore that term, but probably I can lower and upper bound that term. And let us assume that that is possible. I don't know that it's possible, but if it is possible, I assume that there is a lower real number and a higher real number for my psi, and then if I do these, I have here a constant term, and then suddenly I see a differential equation which I can do analytically exactly. That's nice, right? And this is called a Riccati differential equation. And if you solve that Riccati differential equation, you come up with, well, it's probably ugly, but basically it's a very simple form given the complexity of the process I'm describing. You have here an approximation, because now I wrote here the approximation of the real prevalence as a function of an expression which is, again, very simple. This is a tangent H formula, tangent hyperbolicus. But here you only see the parameter t. That's basically an offset. Yeah? And you see two terms here, the capital psi and the capital omega, which are terms which are standard. Well, they are just depending on the coefficients of my differential equations. The c, and you see it happen over again. So, what I showed you, suppose that I can bound this difficult form by a lower and an upper bound real number, then in any graph, right, then I can bound the prevalence in any graph by this one. Yeah? And you see that the difficulties appear suddenly in the C parameters, right? Because I have here, if I substitute here the C by the CU, then I have my upper bound. If I substitute it by the lower bound, then I have here my lower bound. And the real exact one is somewhere in between. Yeah? And it might be equal to. Okay, so that's probably a little bit an error, so it can be equal to.
But it's not that there is bound, it's also constant, right?
Now this is a constant.
C is a constant.
Yeah, this is a constant, yeah. But if in the differential equation you can have a bound and an upper bound of a function which is complex, then you can always write this as a solution. Yeah? So far you roll with me, it gets really difficult for some of the people, but I would show you here something. In 1927, there was a very famous paper which set basically the start of SIR epidemics, that's the Cormick and McKendrick paper, and these have derived and solved the SIR model in a complete graph, basically, assuming that there is no network structure in a complete graph, and they found also a tangent H which is similar to what we have. So if I use here all settings of a complete graph, I have again their initial structure, their initial computations. So, okay, so is this now, this form what I'm going to use, is this useful, right? So if you do simulations, I saw here simulations just to give an idea. The blue curve is the tangent H formula. The red curve are exact, well, are the simulations, and you take this as the difference of things that are exact. So more or less, and if you choose here the C value in such a way that the steady state is precisely okay, then, well, that rough formula, what I call tangent H, is doable. You might learn something about that, right? And that's one of the things what I try to persuade people. If you have a process in which you don't know anything about it, you only know now from that theory one thing, that you can always lower bound and lower bound and upper bound, the real, which is in the blue is, let's say the red curve is the real one of the process, what we know. You can always upper bound and lower bound that process. So in essence, if you have whatever real world prevalence going over time, then you can fit it basically with a very simple tangent H formula, and you get at least 3 parameters. And what's the meaning of those 3 parameters? Well, the meaning of those parameters is related to the effectivity, the tau, the effective tau, and also the underlying structure, which is captured in the eigenvalue structure of the Laplacian. That's what you get. Is it always working? Well, there are cases, and this is a very particular case which was given by Joel Miller to me, because in a paper I wrote that actually the prevalence should be always unimodal, right? So it might always, as a function of time, be 1 maximum and 1 minimum. And basically that's not true. He gave me a counterexample of a very special topology, what you see here. This is a complete graph here, and then a little bit hair and a hairball, and if you infect the nodes all in the outer hairball, then you see that the infection is behaving like this, but with an extremely big variance, right? So that's a very strange topology. And that topology still you can upper and lower bound, but the difference between the lower and upper bound get large. Okay, so this is more or less a little bit publicity why I still think that a simple tangent H formula might be of some use. Okay, let's now move to the more abstract theoretical thing, in which I was inspired by the work of Dimitri working on the geometry of networks, and I try to see how far you can push this. And here this is a little bit related with the geometry of networks. The general universal mean field framework, we've derived this quite lately. We think it's very general, and it contains all methods, mean field methods that are now available. It includes our NIMFA, it includes Alex heterogeneous mean-field, and a lot of other. And we can place bounds on the approximation. And what it uses, basically, we use principles. We use partitioning of a graph. We don't look to one graph, but we look in a partition graph, and I come to that immediately. And then I use 2 steps. I use the closing, moment closing. I said this in the beginning of if you have a differential equation and they are not expressed in all the same functions, then you need to close the equations, and that's important. And then I use, actually, in order to have a feeling of the closing equation, I use the isoperimetric inequality. Okay, that's what I'm now going to explain. First of all, the graph partitioning. We assume that we can always have a graph in K non-overlapping graph, and in any graph we count the infected node in each partition. So why do we do this? Normally in this vector we have n components. If we want to have this is the W vector, the Bernoulli vector, if you would like to have only the infection per node, right? And if we now do the partitions like here, for instance, you have 3 partitions. No? In these partitions, we actually get a smaller vector instead of here, I forgot 9 components. Here I have only 3 components. The only difference is that here I go to 1 and a 0, while now my vector components can change from 0 infected to here maximum 4 infected. The number of nodes that you have here also 4, and here only 1 infected. Okay, this gives you a little bit of sense what I mean by a partition of a graph in K. Well, K is a quantity that you need to choose, and that's probably a little bit the complication, but you can do this. Okay, let's now come back again to the idea of closing the equations. I said to you that this is the exact differential equation, right, what I defined to you on the prevalence. Yeah? And I also said to you that this term was actually an annoying term, which, well, is not of the same form, and I would like to get rid of this. And get rid of this means that I would like to find a function. I would like to replace this term, which is the average fraction of infected links. I would like to replace this by a function of the prevalence itself, right? And that's actually the trick what in, well, often in physics appears that is what people call closing the equations, okay? And how do we do that? Well, we were inspired by, well, a little bit by Dimitri, by the geometry. And if you now look to the geometry, you can say that what we actually do here is, we have here the number of nodes around 2 sets, right? Yeah? And in a more complicated form, you don't see it very well, but this is a very complicated surrounding. This form gives you a little bit more insight, because it's basically in that form as a lattice, or as a, you can talk about the volume here and about the boundary around the volume, right? You can talk about surface and volume, okay? So the idea basically is we are going to replace the surface here, this is the surface, yeah, here around, by the volume. Yeah? And in order to do this, we use the concept of the isoperimetric inequality. You know, those that know a little bit Greek, it comes from isa-periodos, means the same circle meter, right? And then the ancient Greeks got that nice problem of what is now the maximal area given a certain perimeter. And the solution is basically simple in the plane, yeah, that this equation holds for all curves with inequality, and only equality for the circle. I think most of you have learned that on high school, and we thought, yeah, it was simple. But what we didn't know that basically only in the 20th century, the underlying real mathematics has been proven, right? And extended to higher dimensioned curve spaces, manifolds, and graphs. And that's important because we are going to use that concept to the cut set of the graph, right? Because the cut set is annoying, we would like to replace. So this is actually going from volume to surface, or basically I'm going to replace the surface, the infective links, by something of the volume. Okay, that's what it's a good overview what we found lately on the isoperimetric inequality. Now, what we now use for graphs is, this is the number of infective links, and then we are going to use this equation which has been proven by Van Miegham. Yeah? And you see here the eigenvalues of the Laplacian coming in. You see here the average degree of the network. And then you see here a capital, I use now a capital Y, not for the fraction of infected, but a capital Y is now the number of infected nodes. Okay? So here is the number of infective links, and I'm going to approximate, that's the cut set, that's what I don't want, that's an ugly, a difficult thing, which I can't push much further. And I'm going to bound, yeah, you can bound this, so that's also a spectral bound, an upper bound. And of course, the smaller this upper bound is, the better the approximation. Because what I'm going now to do is, I'm going to approximate the infective links by something of the cut set. Right? And what is now nice, basically, is, if you see this formula here, this formula is very, very close, probably you still remember, to the complete graph. Right? So, and in the complete graph, we are very close to exact. Right? And in the complete graph also, we know that, well, mean field is very, very good. Yeah? And this gives also an insight why the complete graph is such a good thing. Another thing what we also came up was that by doing this kind of a bound, you basically tell something about epsilon regularity in the graph. Yeah? You say that the number of links between two partitions in a graph can be approximated by some other constant, smaller or smaller than a kind of an epsilon, which is given, and this is basically what people say, this is epsilon regular. Yeah? The smaller this, of course, is, the better your approximation of the number of links between by this one. And by accident, this is a very fundamental thing on the Szemeredi regularity theory lemma. I'm not going deeper in that lemma because I need another hour to explain deeply what it means, but it's I come to that. Now I'm going to see again our general framework. What I said is I would like to describe the SIS epidemics, right? The number of infected nodes. I split them in two partitions, and if you do it, any of those partitions consist of a consistent and a bipartite graph. And on that bipartite graph that gives you the links between the connections, we are going to use the isoperimetric inequality. If you do that, you need to believe me that then this kind of a differential equation comes out. And that's an approximation, right? That's an approximation. So the complicated term here, this term comes from basically this term here, right? Because this is the average degree, and this is the number of, the same as a kind of an average degree. This is the number of links between the partition K and M, and this is the division by the number of nodes in those partitions, right? So, and again you see that this is the curing term, which is easy for partition A, so one subgraph, and this is the infection, which is due to the other partitions, and if here n is not equal to k, you have a bipartite approximation based on the isoperimetric constant. If n is k, you have the classical approximation. And the classical approximation, probably some of you working in them, then you just have, again, NIMFA. That's the NIMFA equation if n equals to k. Right? So that's on itself already nice. And now I'm going to show for Alex that in the general framework, the heterogeneous mean field is also completely incorporated. The heterogeneous mean field approximation is basically what you do is you are going to focus on the degree distribution rather than on the adjacency matrix or the total topology. You basically do a grouping or a partitioning of all the nodes according to degree, right? So that is the major idea about it. So this is the classical definition that Alex and Romualdo wrote. Yeah? So far, this is again the healing part. It's easy. This is the part if you are not infected. If I'm not infected in probability, not infected, I can get infected. Yeah? And this is all the numbers with degree k. And then the difficult thing is that you have here an additional probability that as a healthy node, I'm connected to an infected node. And they wrote it down in a form, well, that's their formula, but a little bit written in terms of probability distribution. And the nice thing is, if you now substitute this term in here, and you do a simple change of a variable, you can rewrite his equations, these equations, you can write the equations precisely in the framework of the UMF, right? You just write them in the two blocks. Yeah, you see, this is the block of infected in one cluster and not infected in another cluster, and you have here a kind of a connection probability, which in the case of UMF completely depends on the degree. So the UMF model with degree partitioning in the network is precisely the same as the HMF model. So HMF is to some extent contained if you take the degree partitioning, not another partitioning. I thought it was nice to talk to Alex, but because in the past we were always thinking which model is not the best and so on. And another thing what we need to do in the future is, I said that the isoperimetric constant has a bound, that epsilon, right? And the lower that bound, the better your approximation is. And that's the next step to see how good the approximation can be close to, well, with respect to the exact one. But that's for later. Now I would like to close the talk with just the Szemeredi regularity lemma. Yeah? I can only say that's a deep mathematical theorem, but it's I believe it's a kind of the stone of Rosette, right? And it's a little bit a counter thing to the existence of parallel graphs, right? Because it mostly say that any graph can be partitioned in basically subgraphs, and between those subgraphs, the number of links is uniformly distributed, meaning that it's, well, and if you get epsilon more closer and closer, then you have precisely the same number of links between those, and then it gets easier. The more regularity in the structure of your graph, the easier it is. But this theorem also allows you to connect the dynamics of an SIS process with a graph, underlying graph structure, because implicitly you deconform the SIS epidemics into partitions and a cut set all the time. And that's why it might work so well. So I showed very rapidly that epsilon regularity relates to the isoperimetry. I don't know why these people in the Szemeredi lemma didn't make that link, but okay. And we found that the better the isoperimetric inequality works, so for a complete graph it works very well, right? The better the overall approximation of the epidemics in mean-field works, right? So translated on very large graphs, there is always an epsilon similar, a very large graph is epsilon similar to a scale graph, which is much smaller. That's roughly saying, because the details, mathematical details, are huge. And but basically, what I think is in an epidemic process which we've described, the mean-field approximation stands in a relation with isoperimetry and with this very deep theorem that any graph can be partitioned, right, in K clusters all the time, which are regular. Okay, it's heavy already, it's warm outside, I'm going to conclude. So I've shown that the prevalence can be described, and the prevalence is one of the major things. We also call the prevalence the again in statistical theory, the order parameter, right? So, and that's why it's so important to understand that. Then I've given a little bit of propaganda for the tangent H formula. If you have data, right, and you have no clue of the underlying network, you only have a series of data, then I think with that simple formula you can already extract a couple of parameters. And what did that mean? Yeah, then you need to go further. But it's and the formula, what I said, is also already an extension of the Kermack-McKendrick formula. And then we still need to work a little bit deeper on the universal mean-field framework, but I think it gives a feeling why all mean-field models are constrained somehow or another. Okay, this is then the talk, and I need to announce our workshop. We have an epidemic workshop in Delft, August, September. Also Alex is taking there, and Yamir is going to talk. And then a little bit propaganda for my books. And then I stop. Okay, thank you.
Thank you very much, Piet. That was quite a tour de force into the theory. So, is there any question? I can break the ice with one that is a bit general, because you started with the SIS model. The SIS model is a model that has a stationary state. It's not absolute. So, what are the
stable state?
Yeah, that is metastable. It's absorbing metastable, but if you're in the infinite size, it's stable. So what happens with the SIS? So what are the complications that you see in extending this framework to a model like the SIS, so in which there is no station?
No, that's what we also can show. We can extend this to multiple compartments too. So in principle, you can also do it in multiple compartments. We did it before actually with Katerina Scolio, where we called it the Genf model. So you can write the exact equation for a compartment model with n compartments. Yeah, not only two, like SIS. In SIR you have three, but you can think about whatever number of components. And then you can use also mean-field, and in a similar way you can extend it to this one too. The novelty here is not the number of compartments, but the novelty is related with the geometric structure of your group. And I think that absolute regularity and so and there we have the isoperimetric that came to an.
I do not, the issue that with the SIR in a sense change your graph because it has a memory that the SIS doesn't have. No, it's in a sense. That's the point. The SIS at a certain point becomes, it's a problem where it's a, you have recurrent states where the SIR doesn't have recurrent states. When you go through the R, it's done forever. So you are altering your. In a sense, your theorem about the partition changes through the...
That's true. SIR is from a physical point of view different, but from a mathematical point of view it doesn't change so much. And it dies out more rapidly and it doesn't stay in it doesn't have a non-zero steady state. It goes always to zero and it's just a transition. Basically, if you see the tangents H formula, SIR is just the derivative, the time derivative. That's also in Parametric. They did it already on that way. I don't see any more complicated thing from a mathematical point of view. Physically, probably there might be something else.
Yeah, sure. Please go ahead.
So the Szemeredi lemma, right? It's used extensively in graph models, right? But so in the theory of graph limits. But as far as I remember, the proof is extremely non-constructive.
The best proof that I found was in the book of Diestel, and it takes a long time. It takes a complete chapter to prove that. That's one thing. And then the interpretations are given also by Terence Tao. Good interpretations. Interpretations also by Lovac are good, and also in the book of Diestel. And again, that's why I say it's the stone of Rosette. It's not easily, it's counterintuitive in any way, because I find it counterintuitive. In whatever graph you take, you can always find partitions, and you can show them that that the number of links between the. Oh, by the way, Szemeredi doesn't say anything within a partition. It just says between partitions, and that the number of links between the partitions are more or less uniformly distributed. I find that a very exotic.
Yeah, but there is no algorithm to find this.
No. This is mathematics. There exists.
It's non-constructive.
That's true. There exists. That's true, and that's a major complication.
The magic is that you get a scale-free network, for instance, and then you do supernodes. In principle, you can find a partition that is made by supernodes and is an homogeneous graph. So that's if you think it's counterintuitive in a sense.
Yeah, but it's counterintuitive.
It's beautiful, but then it's very hard to use.
I try to make a little bit propaganda to say that you can actually combine most of those mean-field models into one structure just by using this notion. I could never use my model if I couldn't say to you that there always exist k partitions of a network, because then you say, in my graph, k partition doesn't, and then the framework collapses. But now, Szemeredi has proven that it is always possible to do that. And in a sense which is very much related to the isoperimetric, that's what's a little bit triggering for me.
So, what if for discrete dynamics?
You're asking difficult questions. In discrete, I would for discrete dynamics use the embedded Markov chain. So it means that you have to have an essence of the highest possible rate change in your continuous process. If you don't have that, then I see a lot of these equations that says, well, in one time slot, and then they multiply, they assume independence and multiply all the probabilities that I'm not sure. That's what you mean, right?
Yeah.
Then I'm not sure that the whole stuff is still, but that's not pure. There you do already an assumption of independence, and then the discrete Markov chain is not well described from a mathematical point of view in the literature.
And then in connection with that, if you go back to the comparison of the model with the simulations, these are Monte Carlo simulations? Or?
Yes.
So, because Monte Carlo simulation, you would expect that it fits better if you are describing a discrete process. Monte Carlo simulations
Yes.
essentially are discrete
Yes.
dynamics. So my question is this Monte Carlo simulation as we usually do, or you did
Well,
some
what
kind of
we do the Gillespie
Gillespie?
the
Okay,
Gillespie.
so it's one
But we-
transition per unit time.
Yes,
right?
and then we do, to be sure, 1 million or
Yeah, yeah.
100,000 simulations
No, I
to,
was just
to
wondering
wipe
if
out
you-
all statistical fluctuations.
I was just
wipe out.
wondering if the difference was due to the way in which you did the simulations. But
I don't think so.
Any other question? So I think Piet will be still tomorrow, and perhaps if you want to talk to him, you have to contact Dima, because he is in the Department of Physics on campus. But please, if you have any other after talk, please contact him. Thank you very much again.